So let us start with the first formula. Shall we start? So first of all, there are three modes of heat transfer. One is conduction. For conduction mode of heat transfer, what is the governing law? For conduction, what is the governing law? That is Fourier law. You are already aware about that Fourier law. According to Fourier law, Q conduction in x direction is equal to minus K into area normal to the x direction into dt by dx. That is the formula for conduction heat transfer rate, where Ax is the area normal to direction of conduction, and conduction is due to temperature gradient. Area normal to direction of conduction, very, very important. It is always the area which is perpendicular to the direction of conduction. If the conduction is in x direction, A will be the area perpendicular to x direction, normal. And dt by dx is called as temperature gradient in x direction. In x direction, temperature gradient. And K is known as thermal conductivity of the material. K is called as thermal conductivity of the material. What is the unit of thermal conductivity? Thermal conductivity of material. What is the unit of thermal conductivity? If you put all the parameters or unit of each and every parameter, this is Kelvin per unit watt. So the thermal conductivity is watt per meter Kelvin or watt per meter degrees Celsius. That is the conduction heat transfer rate. And as you should know that K is a function of temperature. The thermal conductivity of a material is a function of temperature. So if we show the thermal conductivity versus temperature for liquid and conductor or metal or metals, by increasing the temperature, thermal conductivity decreases, but for gases, insulator or non-metal, the thermal conductivity increases with the rise in temperature, and the thermal conductivity of a gas is directly proportional to root T. For a gas, thermal conductivity will be directly proportional to root T. Right? Then the next mode of heat transfer is convection. What is the governing law for convection? What is the governing law for convection? It is the Newton's law of cooling, isn't it? Newton's law of cooling. According to Newton's law of cooling, Q convection is equal to H into AS into delta T. That is the expression for Q convection, where AS is the surface area. It is the surface area. Duration of the session will be 1.5 hour something. We will try to complete all the formula. Only formula should. So it will be around 1.5 hour. It can go up to 2 hours. We will try to wrap it up by 1.5 hour. All right. Surface area available for convection, or the surface area available for convection is nothing but the surface area in contact with the fluid, isn't it? In contact with the fluid. Because convection is a surface phenomena. So AS will be the surface area which is in contact with the fluid. Fluids are having the convection. And what is delta T? Delta T is called as bulk temperature difference. So if Ts is greater than T infinity, so delta T is equal to Ts minus T infinity. T infinity is the fluid temperature. If Ts is greater than T infinity, or delta T is equal to T infinity minus Ts, if T infinity is greater than Ts. And what is H? H is called as average convective or average convection heat transfer coefficient. The unit of H will be equal to watt per meter square Kelvin or watt per meter square degrees Celsius, right? H is the average value of convective heat transfer coefficient. And one more important thing here is convection can also be known as combined effect of conduction and bulk motion. In the no slip region, there will be conduction. So convection can be termed as the combined effect of conduction and bulk motion of the fluid. So from here we can write H is equal to minus Kf into dt by dy in the fluid at the interface y is equal to 0 upon delta t. That is how we can find out H. H can be calculated by using this formula. Good evening, Surendra. Welcome. Welcome, guys. So minus Kf. Kf is the thermal conductivity of the fluid. dt by dy, temperature gradient in the fluid at y is equal to 0 upon delta t. And this dt by dy can be calculated from temperature as a function of y, and the temperature as a function of y can be calculated from u as a function of y. So the analysis will be part of fluid mechanics. The analysis will go into the fluid mechanics. All right. Now the next mode of heat transfer is radiation. What is the governing law for radiation? Radiation is governed by Stefan-Boltzmann law. Radiation is governed by Stefan-Boltzmann law. According to Stefan-Boltzmann law, heat transfer rate due to radiation for a black body is given by sigma into surface area of the black body into T to the power 4. T is always the absolute temperature. T is the absolute temperature of the black body. Means it is always in Kelvin. Absolute temperature of the black body, it must be in Kelvin. When the temperature is given in degrees Celsius, so temperature in Kelvin is equal to temperature in degrees Celsius plus 273. This is how we can convert the temperature in Kelvin. AS is the surface area available for radiation. Radiation is also a surface phenomena. It is the surface area available for radiation. And sigma is known as, that is given by 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. The sigma is called as Stefan-Boltzmann constant. Sigma is called as Stefan-Boltzmann constant. All right. Now after this, there is another very important expression that is called as energy conservation equation for the system. Energy conservation. And according to energy conservation equation, there are 4 terms: the rate of heat entering into the system plus the heat generated into the system per unit time is equal to the amount of heat leaving the system per unit time plus Q stored in the system. That is energy balance equation for any system. There are 4 terms: heat entering, heat generated, heat out, and heat stored. The heat is stored. When the heat is stored, it changes the internal energy. So it is equal to the rate of internal energy change for the system. Rate of internal energy change for the system. So we can say that is given by Q stored is given by M into C into dt by d tau. M into C into dt by d tau. That is Q stored. Or we can say, so implies T is a function of time. The system is in unsteady state. The system will be in unsteady state. That is about the heat stored. Rate of internal energy change or unsteady state system, there will be heat storage. All are same. Heat leaving from the system can be due to convection, conduction, any mode. What is heat generated? Some other form of energy getting converted into heat energy. So Q generated is equal to Q dot into volume of the system, where Q dot is termed as, Q dot is called as rate of uniform heat generated per unit volume. The unit is watt per meter cube. So this is how energy conservation equation can be written. All right. Clear? What is heat generation? Where some other form of energy is getting converted into heat energy. Some other form of energy gets converted into heat energy in the system, then it is known as heat generation in the system. For an example, electrical energy getting converted into heat energy, that is called as Joule's heating. When the current is flowing in the system will get heated because of conversion of electrical energy into heat energy. That is I square into R. So for electrical energy, for electrical system, we can say Q generated is equal to I square into R. Joule's heating. That is Joule's heating. I is the current, R is the electrical resistance, right? So this is how we can write energy conservation equation. Now let us talk about conduction in plane wall. For a plane wall system, plane wall means the area is constant, and if the thermal conductivity is also constant, thermal conductivity is also taken as constant. So for plane wall, the temperature profile is given by T1 minus T upon T1 minus T2. What is the nature of the temperature profile for plane wall? What will be the nature of temperature profile for the plane wall? That is equal to X by L. The variation of the temperature with X is linear. It will be linear, right? And Q is given by K into A into delta T by L. That can be equated with delta T upon thermal resistance. So where thermal resistance is given by L by Ka. What is the unit of thermal resistance? And the thermal conductance is given by, or it can be written as 1 upon thermal conductance. What is the unit of thermal resistance? Kelvin per unit watt. The unit of thermal resistance Kelvin per unit watt or degree Celsius per unit watt. Delta T is the temperature difference, and similarly another formula Q dash is equal to Q by A, that is equal to K into delta T by L. That can be written as delta T upon A into RTH, where A into RTH is called as unit thermal resistance. This is known as, the unit is meter square Kelvin per unit watt. That is called as unit thermal resistance. Right? It is not watt per Kelvin, Surendra. It is Kelvin per unit watt. यहाँ से देखिए ना, delta T unit Kelvin and divide by Q. RTH is equal to delta T by Q. Right? But all these formula will be valid. Important point is, all these formula which I have mentioned here are valid only when if the system is one dimensional, valid for one dimensional steady state system, steady state without heat generation. The formula will be valid. Yes, it is heat flux. The third formula is for heat flux. That is watt per meter square. The rate of heat transfer per unit area is called as heat flux. So all the formula which I have mentioned here are valid only for one dimensional steady state. Valid for one dimensional steady state without heat generation. Is this clear? Now, if there is a heat generation in the system, If the thermal conductivity is variable, as we know, K is a function of temperature. K is a function of temperature. So dt by dx, will be inversely proportional to K, isn't it? Because Q is equal to minus Ka dt by dx, which will remain constant. Q will remain constant. So dt by dx is inversely proportional to K. Are you able to hear me? I hope you guys can hear me. So if thermal conductivity is variable, then we can draw the temperature profile to be like this. For K is equal to K naught 1 plus minus beta T. So for K naught 1 plus beta T, this is for average thermal conductivity. K is equal to constant, that is equal to K average, and for K is equal to K naught 1 plus beta T. K naught 1 plus beta T, this is the temperature profile, this is T1, this is T2. And for K naught 1 minus beta T, this will be the temperature profile for the plane wall. This is how. And for if K is equal to K naught 1 plus beta T, if you want to find out the average thermal conductivity, so K average is equal to K naught 1 plus minus beta into T average. And what is T average? Where T average is equal to T1 plus T2 by 2. That is how we can find out the average value of thermal conductivity. That is how we can find out, we can write the average value of thermal conductivity. Now the next important thing is heat generation. Plane wall with heat generation. When there is a heat generation, plane wall with heat generation. So when heat is generated, Q dot is constant uniform heat generation. So Q will not be constant, Q will become variable. Whenever there is a heat generation, the rate of heat transfer becomes variable. The rate of heat transfer becomes variable. And if TS1 is equal to TS2, for TS1 is equal to TS2 is equal to TS. If the temperature are same for both the surface, inner surface and outer surface, and if there is a heat generation, then the temperature profile will be, what will be the nature of the temperature profile? What will be the nature of the temperature profile? Tell me, this is x is equal to 0, this is x is equal to L. Area is constant. For TS1 is equal to TS2, this is TS1. This is TS2. What is the nature of temperature profile? Whenever there is a heat generation in the plane wall, the temperature profile will be parabola and the temperature is maximum at the center at x is equal to L by 2. It is parabolic. So T is given by Ts plus Q dot x by 2K into L minus x. That is the formula for temperature profile. Q dot is the rate of heat generation per unit volume. It will be parabolic. The temperature profile will be parabolic. And the heat transfer rate will be linear. Heat transfer rate will be linear. Q is a function of x, will be linear. At x is equal to L by 2, that is the center, T is maximum and dt by dx will be 0. If dt by dx will be 0, so Q will be equal to 0. So T maximum can be calculated from Ts plus Q dot by 8K into L square. That is the formula for maximum temperature, which is at the center. So the direction of heat transfer will be towards left hand side in the first part, towards right hand side in the second part, because the heat transfer always takes place in the direction of decreasing temperature of the system. And if TS1 is not equal to TS2, for TS1 is not equal to TS2, then we can write T maximum to be, if we write TS1 plus Q dot by 8K into twice of L1 square, or we can write TS2 plus Q dot by 8K into twice of L2 square. From here we can find out the maximum temperature. This is the formula for maximum temperature. And if we draw the temperature profile, look, if TS1 is less than TS2, if TS1 is less than TS2, then the temperature profile will be like this. It will be a parabola. Here the temperature will be maximum. This is, we can call this to be L1. We can call this to be L2. So L is equal to L1 plus L2. Or if TS2 is greater than TS1, if TS2 is less than TS1, or TS1 is greater than TS2, TS1 is greater than TS2, this is, let us say, TS1, this is TS2, then the temperature profile will look like this. This is T maximum. This distance is L1. This distance is L2. L1 and L2. Right? So either you can use TS1 or TS2. But if you are using TS1, then 2L1 whole square will be the value. And if you are using TS2, then it will be 2L2 square. I hope this is clear. Now, the plane wall, this is all about the plane wall. These are some of the formula which you must remember for the plane wall. Now, the cylindrical system. One important announcement before we proceed further for the hollow cylinder and hollow sphere. There are three types of system we analyze: plane wall, hollow cylinder, hollow sphere. Plane wall, I have discussed about the three situations. Plane wall with constant thermal conductivity, no heat generation. Then plane wall with variable thermal conductivity, and the third one is the plane wall with uniform heat generation. So tomorrow at 7:30 p.m. Joshit sir will be taking one beautiful special session for securing all India rank under 100 in GATE 2024 examination. It is for GATE 2024, is it? I think it is for 23. I don't know. Please do join this session. You will get some ideas, some things which are important for clearing your GATE examination. All right. So now let us move to the hollow cylinder. In case of hollow cylinder, area which is given by 2 pi r into L, which is not constant. In case of hollow cylinder, area will not be constant. It is a function of r. It is a function of r. 2 pi L is constant, but area will be a function. What is the nature of temperature profile? For a hollow cylinder, can you let me know what will be the temperature profile for a hollow cylinder? What is the nature of temperature profile for a hollow cylinder? For conduction in hollow cylinder? ना ऐसा कि क्या बोल रहे हैं आप? It will be logarithmic. The temperature profile will be logarithmic. The expression will be this. This will be the expression. Then Q is equal to, what is Q? Q is equal to 2 pi KL delta T upon ln of R2 by R1, which can be equated with delta T upon thermal resistance. So the thermal resistance for conduction in case of hollow cylinder is given by ln of R2 by R1 upon 2 pi KL. It will be logarithmic, yes. So this is the formula, and then we define mean area. Do you know the formula for mean area? After this we define the mean area. AM is given by A2 minus A1 upon ln of A2 by A1. That is called as logarithmic mean area for a hollow cylinder to develop the equivalent plane wall. So these formula are again valid. These formula are valid for one-dimensional steady state conduction without heat generation. Conduction without heat generation. Without heat generation, and the thermal conductivity is also taken as constant in the system. I hope this formula you are clear with. Right? Then let us talk about the hollow sphere. Let us discuss some formula for hollow sphere. Hollow sphere. And hollow sphere, again, area which is given by 4 pi r square is not constant. Is not constant. It is a function of. It is a function of r square. It is function of r, or it is a function of r square. So what is the nature of temperature profile for a hollow sphere? What is the nature of temperature profile? T1 minus T upon T1 minus T2. What is the nature of temperature profile? 1 upon R1 minus 1 upon R upon 1 upon R1 minus 1 upon R2. The nature of temperature profile is hyper. Very nice, Naveed. Hyperbolic. The nature of temperature profile is hyperbolic, and the expression is given by this. And Q is equal to 4 pi K R1 R2 delta T upon R2 minus R1. That is the formula for Q, that can be equated with delta T upon thermal resistance for conduction. In case of hollow sphere, then it is given by thermal resistance is given by R2 minus R1 upon 4 pi K R1 R2. That is the formula for thermal resistance. And the next formula is the mean area. Do you know how to find out the mean area for a hollow sphere? If you want to convert it into an equivalent plane wall, then the area will be taken as mean area, that is under root of A1 into A2. That is called as geometric mean area. Again, this formula will be valid for the system one-dimensional steady state conduction without heat generation, and the thermal conductivity is also constant. These are the formula which you should know. Then we can talk about the formula for uniform heat generation in case of cylindrical and spherical system. Do you remember the formula? Give me thumbs up. How many of you remember the formula for heat generation in cylinder and sphere? Good evening, Rishikesh. Welcome. The next is the formula for heat generation. Uniform heat generation. What is the meaning of uniform heat generation? Uniform heat generation means Q dot, rate of heat generation per unit volume, is constant. The rate of heat generation per unit volume is constant. It means the heat is generated uniformly throughout the system. So now if we write for solid cylinder, the temperature profile, what is the nature of temperature profile? Ts plus Q dot by 4K into capital R square minus small r square. That is the formula. That is, the nature will be again parabolic. The nature of very good, Bhaumik, you remember, it is 4K. It is 4K. Right? And at R is equal to 0, it means at the center of the cylinder, temperature will be maximum. So T is maximum, that is given by Ts plus Q dot by 4K into capital R square. Capital R is the radius of the cylinder for a sphere. And also what we can say, and Q is a function of R square. Q will be a function of R square, that is parabolic. Q will be proportional to R square because dt by dr is proportional to R and area is also proportional to R. So it will be function of R square. It will be proportional to R square. Then for a solid sphere, what is the difference between solid cylinder and solid sphere? T is equal to Ts Q dot by 6K. It will be 6K into capital R square minus small r square. And at R is equal to 0, that means the center temperature is maximum. So T maximum is equal to Ts plus Q dot by 6K into R square. R, capital R is the radius. 6K into R square. And Q will be proportional to R cube, cubic. The rate of heat transfer, whenever there is a heat generation, Q will be variable. You know that. Whenever there is a heat generation in the system, the rate of heat transfer becomes variable. The rate of heat transfer becomes variable. Right? So these are the formula for conduction. And after that, let us discuss some formula for the combined modes of heat transfer. When there are multiple modes of heat transfer or circuit diagram, by using the circuit diagram, combined modes of heat transfer. Right? Let us move to the combined modes of heat transfer quickly. As your time is very crucial. For combined modes, what is the meaning of combined modes of heat transfer? When more than one mode of heat transfer are existing. So these are analyzed by electrical analogy or circuit diagram. The analysis will be done by electrical analogy. We will draw the resistance circuit diagram using the resistance series and parallel combination. If there is a conduction, R conduction, conductive thermal resistance is given by L by Ka for plane wall is given by ln of R2 by R1 upon 2 pi KL for cylindrical system and R2 minus R1 upon 4 pi K R1 R2 for spherical system. That is what we have already discussed. 4 pi K R1 into R2. These are the conductive thermal resistance. And for convection, the thermal resistance for convection is given by 1 upon H into AS, where H is convective heat transfer coefficient. And for radiation, thermal conductivity for thermal resistance for radiation is given by 1 upon HR into AS. 1 upon HR into AS. What is HR here? Here H is the convection heat transfer coefficient. The unit is watt per meter square Kelvin. And HR is called as radiation heat transfer coefficient. We define the radiation thermal resistance similar to the convective thermal resistance. Radiation heat transfer coefficient. Again, the unit will be watt per meter square Kelvin. Right? Now, based on these, the resistances can be in series, the resistances can be in parallel. For series combination of resistances, if the resistances are in series, if the thermal resistances are taken in series, then Q will remain constant. Q1 is equal to Q2 is equal to constant. And the thermal potential delta T overall is equal to delta T1 plus delta T2 plus delta T3 and so on. So the equivalent thermal resistance is R1 plus R2 plus R3 and so on. And delta T1 by delta T2 can be written as R1 by R2. These are for series resistances, and for parallel combination of resistances, we can say Q is equal to Q1 plus Q2 plus Q3 and so on. Delta T overall thermal potential is nothing but equal to delta T1 is equal to delta T2 is equal to constant. So 1 upon equivalent thermal resistance will be equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. So from here Q1 by Q2 can be calculated from R2 by R1. Q1 by Q2 is equal to R2 by R1. R is the thermal resistance here. What is R? R is the thermal resistance here. Getting it? I hope this is clear. Any doubt? If anybody is having anything to ask, you can just let me know through the comment section. Now we will move to the more complicated expression, that is composite plane wall with convective environment, let us say. Composite plane wall. What is the meaning of composite plane wall? Where two or more materials are used with convective environment, convection on both sides. Multiple modes of heat transfer, conduction as well as convection, and the system is composite system. For composite system involving combined modes of heat transfer, we can say Q is equal to U into A into delta T over all is equal to delta T over all upon equivalent thermal resistance. Equivalent resistance. That remains constant, where delta T over all is called as overall thermal potential. And from here we can say U into A into R equivalent will be equal to 1. U is called as overall heat transfer coefficient. U is equal to 1 upon A into R equivalent. So U is called as overall heat transfer coefficient. अजय कृष्णा, मैंने उस पे लिखा था earlier it was supposed to be at 10:30 only, but we have shifted it to, because 11:15 Dheeraj sir will be having another session, so it was getting clashed, so that is why we kept it at 9. Okay. So U is the overall heat transfer coefficient, that is 1 upon A into R equivalent, where and R equivalent will be given by 1 upon A into 1 upon HI, inner convective heat transfer coefficient, plus Lj by Kj, J is equal to 1 to N, plus 1 upon H naught. This is how we can write. Right? Delta T overall is overall thermal potential, that is Ti minus T naught. So this is R equivalent. We can find out U. We can find out U from here. That is for composite plane wall with convective environment. Similarly, we can write the expression for composite cylinder with convective environment. Similarly, we can write the formula for composite cylinder with convective environment. Composite cylinder. So again, Q will remain constant because there is no heat generation, there is no heat stored. As long as heat generation and heat stored is 0, Q will remain constant. That is equal to Ui into Ai into delta T overall is equal to U naught into A naught into delta T overall is equal to delta T overall thermal potential upon equivalent resistance. That will remain constant. That will remain constant. From here we can say Ui into Ai into R equivalent is equal to U naught into A naught into R equivalent will be equal to 1, and Ai is equal to 2 pi R1L and A naught is equal to 2 pi R n plus 1 into L. Isn't it? If there is 2 layers, then n will be the number of layers. N will be the number of layers. For 2 layers, the outer radius will be R3. For one cylindrical system, for one hollow cylinder, outer radius will be R2. For 2 layers, outer radius will become R3. For 3 layers, outer radius will become R4. So A naught is equal to 2 pi R n plus 1 into L. L is the length. And from here we can say ui is equal to 1 upon ai into r equivalent. We can find out ui, and similarly we can find out u naught is equal to 1 upon a naught into r equivalent. ui and u naught are the inner overall heat transfer coefficient and outer overall heat transfer coefficient. ui and u naught are inner and outer overall heat transfer coefficient. And what is r equivalent here? Equivalent is equal to 1 upon 2 pi L into 1 upon hi into r1 plus summation of ln of rj plus 1 upon rj divided by kj plus 1 upon h naught into rn plus 1. This will be the expression for equivalent resistance, right? Similarly, we can write the formula for composite sphere. Everything else is same. Composite sphere with convection environment. The variable parameters is ai will be equal to 4 pi r1 square and a naught will be equal to 4 pi r n plus 1 square. And we can say q is equal to ui into ai into delta t overall is equal to u naught into a naught into delta t overall is equal to overall thermal potential upon thermal resistance that remains constant. So ui and u naught are inner and outer overall heat transfer coefficient. We define overall heat transfer coefficient, the unit will be watt per meter per Kelvin. So here the thermal resistance will be equal to, what is the thermal resistance? 1 upon 4 pi, then 1 upon hi into r1 square plus summation of rj plus 1 minus rj upon kj into rj plus 1 kj rj plus 1 plus 1 upon h naught into rn plus 1 square. This is the equivalent thermal resistance. This is the equivalent thermal resistance. Got it? Getting it or not? So that completes our discussion for conduction in plane wall, conduction in cylindrical system, and conduction in spherical system. If anybody is having any doubt, you can just let me know. This is all about the conduction mode of heat transfer with heat generation and without heat generation. Anybody is having anything to ask? Bataiye, is it all fine with everyone? The session is, let me clear you, this session is only to discuss the formula, important formula, which we must memorize. Now let us talk about the insulation method. There are two methods for increasing the rate of heat transfer. One is the insulation method. The another method is by using the fin. So we will talk about these two methods for increasing the rate of heat transfer in a system. The insulation method can only be increasing the heat transfer rate in radial system. It cannot increase the rate of heat transfer in case of radial system. In plane wall system. In case of plane wall, the insulation method will not improve the rate of heat transfer, but in radial system, it increases the rate of heat transfer. And the fin theory can be applicable to any type of system, whether it is radial or plane wall system. And then we will be talking about the unsteady state conduction. That will complete our 60% of our syllabus. Once the conduction is over, complete conduction, then it covers the 60% of the syllabus. So you can see there is an important information here in this slide. There will be 3 consecutive sessions from 27th, 28th and 29th of January for verbal ability, engineering, mathematics and general aptitude. So do not forget to join these sessions. They are very, very beneficial for the last moment revision of aptitude, verbal ability and mathematics. They can improve your score by 2, 3, 4, 5 marks. So that will be very, very important. in gate examination. All right. So let us talk about the critical radius of insulation. For increasing the rate of heat transfer, we use the critical insulation method. What is the critical radius of insulation? What is the formula for critical radius of insulation? What is the formula for critical radius of insulation? Can anybody let me know? That is used in radial system. Now you should always remember critical radius of insulation is thermal conductivity of insulating material upon outer convective heat transfer coefficient. That is for cylinder. If the system is in the form of a cylinder, K by H. IES का तो आफ्टर गेट एग्जामिनेशन है ऋषिकेश. अच्छा, आप किसकी बात कर रहे हैं? नॉन टेक का रिवीजन की बात हो रही है ना. आर इंसुलेशन फॉर स्पेरिकल सिस्टम ये होगा ट्वाइस ऑफ के बाई एच नॉट outer convective heat transfer coefficient. And there is a term that is called as critical thickness of insulation. So many people commit mistake here. This is called as critical thickness. If the question is asking critical thickness or critical radius, you should be clear with that. It is critical thickness of insulation. हाँ, अभी बताते हैं. अभी मैं स्लाइड दिखाऊंगा ऋषिकेश उसके बारे में भी. TCR is the critical thickness of insulation, that is RCR minus R naught. Now, if R naught is less than RCR, अगर R naught की वैल्यू RCR से कम है, जैसे मान लीजिए ये है RCR, that is RCR. At RCR, the heat transfer will be maximum and then it will decrease. If R naught is less than RCR, then by insulation, with insulation, heat transfer rate increases first. If R naught is less than, R naught is the outer radius of the system, radial system, then with insulation, Q increases first, becomes maximum, and then decreases. Then decreases with the further increase in insulation. With increasing insulation. If R naught is less than RCR. But if R naught is greater than equal to RCR, if R naught and RCR equal, then with insulation, what will happen? Then with insulation, Q will decrease continuously. यहां से भी क्वेश्चन आते हैं. Q will decrease continuously. Q will decrease continuously. Right? So this is all about the insulation method. Now the second method is the fin theory. The first method is insulation method to increase the rate of heat transfer. The second method is the fin theory. There are three types of fin we discuss. In fin theory, there are three types of fin. Very long fin. When L is very large, the length of the fin is very large. The second case is short fin with insulated tip. And the third case is short fin with free tip, insulated tip. So first of all, let us talk about very long fin. What is the nature of temperature profile if the length of the fin is very large? What is the nature of temperature profile? Theta upon theta s. That is T minus T infinity upon Ts minus T infinity. What is the nature of temperature profile? e to the power minus mx, that is exponential. The temperature profile is exponential. Yes. The temperature profile will be exponential, where m is equal to under root of hp by k into cross-sectional area. This is called as Finn constant. Finn constant or Finn coefficient. This is known as Finn constant or coefficient. The unit is meter inverse. That is called as Finn constant or Finn coefficient. The unit is meter inverse. And we can write Q Fin. Q Fin is equal to Ka m into theta s, or we can write it as under root of Hp k into a into theta s. So from here we can say Q Fin is directly proportional to root k. Q Fin will be proportional to root k, isn't it? Ka m theta s. Put the value of m under root of Hp by k. P is the perimeter. P is the perimeter. AC is the cross-sectional area. Area of the fin. This is how we can find out Q, heat transfer rate. Then we define the fin efficiency. Efficiency of the fin. Fin efficiency, that is equal to Q fin upon Q maximum. That will be given by 1 upon ml, because Q maximum is equal to H into P into L into theta s. That is called as thermal performance, and efficiency of the fin is always less than 1. Fin efficiency is always less than 1. One upon ml, which is less than 1. Maximum is 1. Then fin effectiveness. Effectiveness of the fin, that is Q fin divided by Q without fin. That is equal to, what is the formula? Km by H. It can be less than equal to greater than 1. And what is Q without fin? Q without fin is equal to A into AC into theta s. So that will be given by Km by H. This is called as fin effectiveness. This is called as fin effectiveness. This is called as fin efficiency. Fin effectiveness, fin efficiency. These are the formula for very long fin. Fin efficiency is the thermal performance. Fin efficiency is defined for thermal performance. And fin effectiveness is defined for economic performance. Then short fin with insulated tip. What is the nature of temperature profile? Short fin with insulated tip. So theta upon theta s, which is T minus T infinity upon Ts. Ts is the surface temperature minus T infinity, is equal to cos of hyperbolic m L minus x upon cos hyperbolic ml. That is hyperbolic. The nature of temperature profile will be hyperbolic, and at x is equal to L, at the tip, theta will be minimum. So Q will be 0, or d theta by dx will be 0, or we can say Q will be 0. Q at tip will be equal to 0. So theta minimum can be calculated, theta minimum upon theta s. That is equal to 1 upon cos of hyperbolic ml. And we can write Q fin. Q fin is equal to Ka m theta s into 10 hyperbolic ml. And we can write efficiency of the fin is equal to 1 upon ml into 10 hyperbolic ml, and the next formula, effectiveness of the fin is equal to km by h into 10 hyperbolic ml. These will be the formula for short fin with insulated tip. And for short fin with free tip, let me write B here. This is B, this is formula 1, this is formula 2, this is formula 3. And the short fin with free tip is for short fin with free tip, then L is replaced by LC, that is equal to L plus AC by perimeter, that is called as character length. L will be replaced by LC, that is called as character length in our previous formula. Put L by LC in previous formula. For previous formula, in previous formula. For an example, if we write theta by theta s, then we will write cos hyperbolic m LC minus x upon cos hyperbolic m into LC. This Q fin is equal to, Q fin will be equal to KAM theta s into 10 hyperbolic m LC. This is how the formula will be replaced for short fin with free tip. These are the formula for short fin with all the previous formula. In all the previous formula, we can replace L by LC. So that completes our fin theory. The next is unsteady state conduction. The next is unsteady state conduction when temperature is a function of time. When the temperature is a function of time. So for our conductive thermal resistance for the solid to be less than equal to 1/10 of R convection for the fluid. Or we can say for Biot number less than 0.1, it is called as lump system analysis. The analysis is known as lump system analysis. We call it as when the conductive resistance is less than 1/10 of convective resistance. The analysis is called as lump system analysis. It means temperature will be a function of time only. Temperature of the system will be a function of time only when the Biot number is less than 0.1 or the conductive thermal resistance is less than 1/10 of convective thermal resistance. So the formula can be written as, the first formula can be written as theta upon theta I is equal to T minus T infinity upon Ti minus T infinity is equal to e to the power minus AS upon rho CV into tau. That is e to the power minus B into tau. Or we can write e to the power minus tau upon tau star, or we can write e to the power minus Biot number into Fourier number. That is exponential. The temperature profile is exponential. Ti is the initial temperature of the system, and T is the temperature at any time. AS is the surface area, and V is the volume of the system. H is convective heat transfer coefficient, tau is the time, T is the temperature. T infinity is the fluid temperature. T infinity is the fluid temperature in which the system is kept. So the term defined here is, there is a term defined that is called as tau star, that is 1 by B is equal to rho CV by H into AS. That is called as time constant of a thermocouple. This is known as time constant. The unit is second. And what is B? B is equal to HA by rho CV. The unit is second inverse. That is called as thermal response of the system. Time constant is inversely proportional to thermal response. So there are dimensionless numbers defined. One is called as Biot number. The ratio of conduction thermal resistance for the solid to the convective resistance for the fluid is called as Biot number. That is H into LB by K. HLC by K, where K of solid, where LC is equal to volume per unit surface area. That is called as characteristic length. Volume per unit surface area. Volume per unit surface area is LC. That is known as characteristic length. And the next dimensionless number is called as Fourier number. What is Fourier number? Fourier number is the ratio of conductive resistance to the, or Q conduction upon Q stored. The ratio of conductive heat transfer rate to the rate of thermal energy stored in the system. So it is given by alpha tau by LC square. LC is the characteristic length, which is volume per unit area. Alpha tau by LC square, where alpha is equal to K by rho C. K of solid. K by rho C. Alpha is called as thermal diffusivity of the system. That is the property. Alpha is the thermal diffusivity. Do you know the unit of alpha? What is the unit of alpha? What is the unit of alpha? And Q can be calculated. Q, heat transfer rate at any instant, that is H into A into T minus T infinity, that is equal to minus rho CV into dt by d tau. That is how we can find out the heat transfer rate. And Q maximum is equal to H into AS into Ti minus T infinity. Sorry, it is not HA. It is MC into Ti minus T infinities. It is not small q. It is Q maximum. Maximum heat transfer rate. Maximum amount of heat transfer is equal to M into C into Ti minus T infinity. The unit is joule. The unit is, yes, now wait, the unit is meter square per second. That is about the lump system analysis. All right, these are the formula for lump system. This is the only important and a steady state conduction. Now let us move to the next part, that is convection. Now three topics are left: convection, radiation, and heat exchanger. So we will try to complete in the remaining formula in the next half an hour. Yes, Rishikesh, this is the information for non-tech marathon for ESC prelims starting from 13th of Feb. Are you there, Rishikesh? From 13th of Feb. The marathon session for non-technical portion of engineering services examination will be starting on BYJU'S YouTube channel. All right. Now let us talk about the convection. There are two types of convection. One is forced, or also called as artificial. Another is free or natural convection. Forced or artificial convection, free or natural convection. Now, in case of forced convection, the fluid is forced to flow. The fluid is forced to flow. So there are pressure gradient and inertia force. So in case of forced convection, Nusselt number is a function of Reynolds number multiplied by a function of Prandtl number. Nu is called as the Nusselt number. Nu is the Nusselt number. So Nusselt number is given by the ratio of conductive thermal resistance in the fluid to the convective thermal resistance in the fluid. The ratio of conductive to convective thermal resistance, that is HL by Kf, thermal conductivity of the fluid. That is the difference between Biot number and Nusselt number. In Biot number, the conductive resistance is for, or we can also write it as Q convection divided by Q conduction. If it is the ratio of heat transfer rate, then it is convection divided by conduction. But if it is the resistance, then it is. And what is the Prandtl number? This is the Nusselt number. And PR is kinematic viscosity by alpha, mu into Cp by Kf. That is called as Prandtl number. Prandtl number, where mu is the dynamic viscosity of the fluid. And Re is the Reynolds number, you all know, ratio of inertia force by viscous force. That is called as the Reynolds number. So this is about the forced convection. Now forced convection can be divided into two parts. One is external forced convection. When it is external forced convection, when the fluid is forced to flow over a surface, that is analyzed by boundary layer theory. Boundary layer theory. One is laminar boundary layer. For laminar boundary layer, when the Reynolds number, local Reynolds number is less than 5 into 10 to the power 5. So the boundary layer growth will take place like this. For laminar boundary layer, it will be like this. And in turbulent, it will be a single curve. Here it will be two curves. In laminar region, this is laminar, this is turbulent. This is the transition. So this is how the growth of boundary layer will take place. For Prandtl number, for laminar boundary layer, if Prandtl number is less than 1, Prandtl number is less than 1 implies delta V, velocity boundary layer thickness, is less than delta T, thermal boundary layer thickness. If Prandtl number is equal to 1, then delta V is equal to delta T. If Prandtl number is greater than 1, then delta V is greater than delta T. Very, very important. We need to find out the Prandtl number, and based on Prandtl number, we can say if it is less than 1, then delta V. Delta V is the velocity boundary layer thickness in laminar region. Velocity boundary layer thickness, or we can call it as hydrodynamic boundary layer thickness. Delta T is called as thermal boundary layer thickness. Delta T is the thermal boundary layer thickness. Further, we develop the formula. Delta V, velocity boundary layer thickness, is 5x upon under root of Rex. So delta V is directly proportional to root x. Velocity boundary layer thickness is directly proportional to root x. First formula for laminar boundary layer. The second formula we can write delta V by delta T is equal to Prandtl number to the power 1 by 3. Delta V by delta T is equal to Prandtl number to the power 1 by 3. The third formula, local friction coefficient, that is tau naught upon rho u infinity square by 2 is equal to 0.664 upon under root of Rex. So we can say Cfx is proportional to x to the power minus 1 by 2. That is called as local friction coefficient. And CD is equal to average drag coefficient. CD will be equal to, from here we can write CD is equal to twice of Cf at x is equal to L. That is called as average drag coefficient. Average drag coefficient. And then next formula is Nusselt number, that is Hx into x by Kf is given by 0.332 into Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. I should have mentioned here for laminar boundary layer. So Nusselt number is directly proportional to Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3 for laminar boundary layer. And the exact expression is this. So we can say Hx is proportional to x to the power minus 1 by 2. And h bar is equal to twice of h at x is equal to L. And average Nusselt number is twice of Nusselt number at x is equal to L. This is called as average convective heat transfer coefficient. Average convective heat transfer coefficient. These are the formula you should have known. All right. Now let us move to the turbulent boundary layer. Are these formula clear or not? बताइए इनमें laminar boundary layer, these formula you should memorize, you should remember. Anybody is having any doubt, anything to know, you just let me know. Then the turbulent boundary layer, when the Reynolds number is greater than 5 into 10 to the power 5, then we can say Nusselt number is proportional to Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. That will be the expression. So the first formula is delta V is equal to delta T, that is 0.376 x upon under root of Rex to the power 1 by 5. So from here, delta V is equal to delta T is proportional to x to the power 4 by 5. Will be proportional to x to the power 4 by 5. And the next formula is Cfx is equal to 0.059 upon Rex to the power 1 by 5. So Cfx is proportional to x to the power 1 minus 1 by 5. And CD is equal to 5 by 4 Cf at x is equal to L. That is the average drag coefficient. Then the Nusselt number, that is Hx into x by Kf is equal to 0.03 into Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. So from here we can say Hx is proportional to x to the power minus 1 by 5, isn't it? And the average convective heat transfer coefficient is 5 by 4 into Hx at x is equal to L. Average value of Nusselt number is 5 by 4 into Nusselt number at x is equal to L. These are for turbulent boundary layer. Do you know these formula or not? That is for external force convection. Now let us talk about the internal force convection. For internal force convection, flow in pipe or duct, flow in pipe or flow in a duct. So Reynolds number is given by rho into average velocity into dh by mu, where dh is called as hydraulic diameter 4a by p. That is called as hydraulic diameter. Non-circular pipe can be replaced by a circular pipe by using the hydraulic diameter. Hydraulic diameter. And average velocity can be defined as 2 by r square integration of 0 to r u, which is a function of r, into r dr. And the average temperature or bulk mean temperature 2 upon v average r square integration of 0 to r u, which is a function of r, t as a function of r, into r dr. So mean temperature and mean velocity can be defined like this. This is the bulk mean temperature. That is the bulk mean temperature. Then we also define the energy equation. Now look, energy equation, how to write the energy equation. If this is a pipe, this is section 1, this is section 2. So we can say Q is equal to H into A, or H into pi dl into TS average minus TB average is equal to M mass of the fluid into C for the fluid into TB2 minus TB1. So TB average will be equal to TB1 plus TB2 by 2. That is the energy conservation equation. The heat transfer rate, the rate of heat transfer is equal to increase in internal energy. The heat transfer rate will be equal to increase in its internal energy, right? Now for laminar boundary layer or laminar flow, when the flow is laminar, when the Reynolds number is less than 2000, then we can say Nusselt number is equal to H into D by Kf is equal to, it will be 4.36 for Q dash to be constant for constant wall heat flux, and it will be 3.66 for surface temperature to be constant. The value will be constant. The value of constant will be 4.36 for constant heat flux condition, and the value will be 3.66 for constant surface temperature. And for turbulent, let me write for turbulent. From here we can say H is proportional to D to the power minus 1. H will be proportional to D to the power minus 1. And for turbulent flow, when the Reynolds number is greater than 4000, in that case, when the Reynolds number is greater than 4000, then Nusselt number is given by H into D by Kf is equal to 0.023 into Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. For turbulent flow, Nusselt number is directly proportional to Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. And for laminar flow, Nusselt number is constant. Nusselt number is constant. So what is the relation between H and D? D to the power minus 1 by 5, isn't it? H will be proportional to d to the power minus 1 by 5. And then we talk about the natural convection. Natural convection. In case of natural convection, Reynolds number is replaced by Grashof number. Reynolds number will be replaced by Grashof number. Nusselt number is a function of Grashof number into multiplied by a function of Prandtl number. That is due to density gradient. अच्छा कल्याण, हाँ एक्चुअली देयर इज, आप रिकॉर्डिंग देख लेना, इट एट द लास्ट मोमेंट इट गॉट रीशेड्यूल्ड. डेंसिटी ग्रेडियंट एंड बाइंड फोर्स. Bind force, density gradient and bind force. What is Grashof number? Grashof number is the ratio of bind force to the viscous force. So this is given by rho square g beta delta t x cube by mu square. That is the local Grashof number. Or we can write it as g beta delta t lc cube by x cube by mu square. Nu square. Nu square. That is called as local Grashof number. That is called as local Grashof number. Grashof number. And beta is called as, that is equal to 1 upon film temperature, where film temperature is equal to Ts plus T infinity by 2 for ideal gas. That is called as coefficient of thermal expansion. Beta is called as coefficient of thermal expansion or volumetric expansivity. Beta is called as coefficient of thermal expansion, or we can call it as volumetric expansivity. The unit is, what is the unit of beta? Kelvin inverse. And x is, and the average Grashof number, we define the characteristic length. For average Grashof number LC is equal to rho square g beta delta t LC cube by mu square, where LC is called as characteristic length. What is characteristic length? The length over which boundary layer is allowed to grow. It is the length over which boundary layer is allowed to grow. Or thermal boundary layer is allowed to grow. The length over which the thermal boundary layer is allowed to grow. Allowed to grow. That is called as characteristic length. Now, important portion is for laminar boundary layer. For laminar boundary layer, when the Grashof number is less than 10 to the power 9, so Nusselt number is proportional to Grashof number multiplied by Prandtl number to the power 1 by 4. And Grashof number into Prandtl number is called as Rayleigh number. Rayleigh number. And for turbulent boundary layer, क्या होगा formula? For turbulent boundary layer, when the Grashof number is greater than 10 to the power 9, Nusselt number is proportional to Grashof number into Prandtl number to the power 1 by 3. That is the difference for turbulent and laminar boundary layer. That is for natural convection. These are the formula for natural convection. That completes our discussion for convection. These are some of the important formula, or most of the formula I have already discussed. These are the formula for convection. Next is heat exchanger. Next is heat exchanger. Q is given by CH into delta TH, or we can write Cc into delta Tc, or we can write U into A into delta Tm, or we can write effectiveness into Q maximum. That is how we can find out the thermal capacity of the heat exchanger. That is the thermal capacity of the heat exchanger. Where C is capital C is equal to mass flow rate into specific heat. That is called as heat capacity rate. That is known as heat capacity rate. The unit is watt per Kelvin. Where C is called as specific heat. That is joule per kg Kelvin. And what is delta TH? Here delta TH is equal to TH1 minus TH2, and delta TC is equal to TC2 minus TC1. U is the overall heat transfer coefficient. Q maximum, epsilon is effectiveness. Q maximum is equal to C minimum into TH1 minus TC1. 1 for inlet, 2 for outlet. Inlet temperature is 1. Outlet temperature will be 2. And where C minimum is minimum among CH and CC. And what is delta Tm? What is delta Tm in this expression? Epsilon is effectiveness. What is delta Tm? Delta Tm, which is delta Ti minus delta Tf upon natural log of delta Ti by delta Tf. That is called as logarithmic mean temperature difference. This is LMTD. That is called as logarithmic mean temperature difference, or we can call it as LMTD. For parallel flow heat exchanger, ये formula याद होने चाहिए. If it is parallel flow heat exchanger, this is how the temperature curve is. This is TH1, TH2, TC1, TC2. That is parallel flow. This is delta Ti और ये है delta Tf. So for parallel flow, delta Tm for parallel flow heat exchanger, we can write delta Ti is TH1 minus TC1 minus TH2 minus TC2 upon natural log of TH1 minus TC1 divided by TH2 minus TC2. For counter flow heat exchanger, this is TH1, TH2, here TC1, here TC2. ये है delta Ti, ये है delta Tf. So delta Tm for counter flow heat exchanger is equal to TH1 minus TC2 minus TH2 minus TC1 upon natural log of TH1 minus TC2 upon TH2 minus TC1. That is for counter flow heat exchanger and parallel flow heat exchanger. And for a counter flow heat exchanger, if CH is equal to CC, or we can say delta TH is equal to delta TC, then the temperature profile will be straight lines like this. This is TH1, this is TH2, this is TC1, this is TC2. In this case, this is the special case of counter flow heat exchanger. From the L hospital rule, delta Tm will be for this counter flow heat exchanger is equal to delta Ti is equal to delta Tf. This is delta Ti, this is delta Tf. So that is equal to, either we write TH1 minus TC2, or we can write this is delta Tm, mean temperature difference, or we can write TH2 minus TC1. This is the special case of counter flow heat exchanger. That is a special case of counter flow heat exchanger. And for complex heat exchanger, there is a parameter defined that is called as LMTD correction factor. So delta Tm for a complex heat exchanger. What is a complex heat exchanger? It can be multi-pass or cross flow heat exchanger. So it is given by F into delta Tm, mean temperature difference, for counterflow heat exchanger, where F is called as, which is less than 1, that is called as LMTD correction factor. F is called as LMTD correction factor. All right. Now effectiveness in terms of NTU. उसके बाद the last part is effectiveness of a heat exchanger, that is Q upon Q maximum. What is effectiveness? Q upon Q maximum. Q actual by Q maximum. Effectiveness of a heat exchanger is equal to the ratio of actual heat transfer rate to the maximum possible heat transfer rate, and Q will be maximum for a counterflow heat exchanger if TH1 is equal to TC2 or TH2 is equal to TC1. And now effectiveness in terms of NTU. If we develop the formula for effectiveness in terms of NTU, number of transfer units. So the formula for effectiveness in terms of NTU, one is effectiveness for parallel flow heat exchanger, 1 minus e to the power minus n 1 plus c upon 1 plus c, where n is equal to UA by C minimum, that is called as number of transfer units, and C is equal to C minimum by C maximum. This is called as heat capacity ratio of heat capacities, and N is NTU, number of transfer units, UA by C minimum, that is for parallel flow heat exchanger. And effectiveness for counterflow heat exchanger is given by 1 minus e to the power minus n 1 minus c upon 1 minus c e to the power minus n 1 minus c. These are the formula for parallel flow heat exchanger and counterflow heat exchanger. And for complex heat exchanger, it is multiplied by effectiveness for complex heat exchanger is equal to effectiveness correction factor into effectiveness for counterflow heat exchanger. Now a special case. Some special cases. First one, if C is equal to 0, if there is a phase change, in any one of the fluid, then C will be equal to 0. It is either boiler or condenser. So in that case, effectiveness for parallel is equal to effectiveness for counter is equal to effectiveness of complex. That is equal to 1 minus e to the power minus n. If C is equal to 1, if CH is equal to CC or delta TH is equal to delta TC. अगर C is equal to 1 है, then effectiveness for parallel is given by 1 minus e to the power minus 2n by 2. But effectiveness for counter, that is calculated from L'Hospital rule, that is 1 upon n plus 1. N upon n plus 1. That is calculated by L'Hospital rule. This is important. If C is equal to 1, if there is a phase if CH is equal to CC or CH is equal to CC or delta TH is equal to delta TC. Then let us talk about the radiation mode of heat transfer. That completes our discussion for heat exchanger, and the last part is the radiation. Let us discuss some formula from the radiation as well. जो सबसे इंपॉर्टेंट फॉर्मूला सबसे पहला जो फॉर्मूला है दैट इज जे रेडियोसिटी इज एप्सिलॉन ईबी प्लस जी. That is the radiosity watt per meter square. That is the relation between radiosity, emissive power, and insolation. Sorry, it will be plus rho g. Sorry, epsilon EB plus rho g. So J can be less than equal to greater than G. For J less than equal to G, if J is less than G, then there is net heat gain. The system, the body will have a heat gain, that is Q by A gain is equal to G minus G. If J is greater than G, then there will be net heat loss. The system will be having a heat loss, that is J minus G. And if J is equal to G, there is no heat gain or no heat loss. In that case, Q by A will be equal to 0. Q by A will be equal to 0. So there is a surface, opaque surface. The incident radiation is G. The reflected radiation is rho into G, and then emitted radiation is epsilon EB. So this combined together is called as radiosity. This is called as radiosity G. And the next is from energy conservation equation. Alpha plus rho plus tau is equal to 1 for any surface emitting any type of radiation. The sum of these radiation properties will be equal to 1. Alpha plus rho plus tau is equal to 1. That is from the energy conservation equation. And the shape factor F1 to 2 is equal to Q1 to 2 upon Q1. That is called as the radiation shape factor. From the reciprocity theorem, this radiation shape factor can be written as A1 F1 to 2 is equal to A2 F2 to 1. A2 F2 to 1. F1 to 2 is not equal to F2 to 1. From enclosure theorem, F11 plus F12 plus F13 is equal to 1. Enclosure theorem. And the self shape factor F11 is equal to 0 for a flat surface or a convex surface. Self shape factor F11 is not 0 for a concave surface. The surface is concave, the self shape factor is not 0. That is the shape factor. F is called as shape factor. Radiation shape factor I have already mentioned. Then some radiation laws. One is Planck distribution law. It is about E lambda B, monochromatic emissive power of the black body. Then Stefan-Boltzmann law. That is about EB, total emissive power of the black body, that can be obtained from E lambda B into D lambda integration. That is area under spectral distribution curve for emission. Then Wien displacement law. According to Wien displacement law, lambda maximum into temperature is equal to constant. That is called as Wien displacement law. Then Kirchhoff's law of radiation. Kirchhoff's law of radiation. Epsilon is equal to alpha. Epsilon is equal to alpha for temperature to be constant. If a body is in thermal equilibrium with its surrounding, then epsilon will be equal to alpha. Then Lambert cosine law, that is about intensity. Intensity in any direction is directly proportional to cos theta. So these are some radiation laws. And the next is the radiation analysis. The last part is radiation analysis or radiation heat exchange between two or more bodies. Between black bodies, there is this is analyzed by circuit diagram, electrical analogy. So for black body, radiation for the black body, there is a term defined that is called as space resistance, that is equal to 1 upon A1 F1 to 2. That is called as space resistance between two bodies. RS, or we can call it as R1 to 2, that is 1 upon A1 F1 to 2, or we can write it as 1 upon A2 F2 to 1. That is the space resistance between 1 and 2. The space resistance between 1 and 2. The unit is meter to the power minus 2. So for the black bodies, we can say Q1 to 2 net is equal to delta EB upon RS. That is equal to sigma into T1 to the power 4 minus T2 to the power 4 upon 1 upon A1 F1 to 2. That is called as, that is the formula for net radiation heat exchange. That is the formula for net radiation heat exchange between the black bodies. That is the net radiation heat exchange between 1 and 2. For non-black bodies, there is one more resistance defined. For non-black bodies, there is a term defined that is called as surface resistance, or R1 is equal to 1 minus epsilon 1 upon epsilon A. That is called as surface resistance. For black bodies, surface resistance will be 0. For black bodies, surface resistance, that is 1 minus epsilon 1 upon epsilon A, is equal to 0 for the black body. For the black body, surface resistance will be 0, but here there will be surface resistance. So we can say Q1 to 2 net is equal to delta EB upon the surface resistance for body 1, space resistance between 1 and 2, plus the surface resistance for body 2. That is sigma into T1 to the power 4 minus T2 to the power 4 is the numerator. 1 minus epsilon 1 upon epsilon 1 A1 plus 1 upon A1 F1 to 2 plus 1 minus epsilon 2 upon epsilon 2 A2. This is the formula. Or we can write it as sigma into A1 into T1 to the power 4 minus T2 to the power 4 upon 1 minus epsilon 1 upon epsilon 1 plus 1 upon F1 to 2 plus A1 by A2 into 1 minus epsilon 2 upon epsilon 2. That is Q1 to 2 net. There will be three resistances in series, and for infinitely large parallel plates, so it can be treated as two surface enclosure. For two surface enclosure, A1 will be equal to A2 is equal to A, and F11 is equal to 0 is equal to F2 to 2, or we can say F1 to 2 is equal to F2 to 1 is equal to 1. If we put the values in the previous equation, then we can say Q1 to 2 net is equal to sigma into A into T1 to the power 4 minus T2 to the power 4 upon 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Or we can say Q dash is equal to Q by A. That is the flux. Radiation heat flux. The unit is watt per meter square. Similarly, for long hollow cylinder or long concentric cylinders, A1 is equal to 2 pi R1L, A2 is equal to 2 pi R2L, and F11 or F122 is equal to 1 because F11 is equal to 0. Inner cylinder will have 0 because inner cylinder is convex surface. So the shape factor for inner cylinder will be 0. So Q122 net can be written as sigma into 2 pi R1L into T1 to the power 4 minus T2 to the power 4 divided by 1 upon epsilon 1 plus R1 by R2 1 minus epsilon 2 upon epsilon 2. That is the expression. And similarly for hollow sphere or concentric sphere, concentric spheres, so Q122 is equal to sigma into 4 pi R1 square into T1 to the power 4 minus T2 to the power 4 upon 1 by epsilon 1 plus R1 square by R2 square into 1 minus epsilon 2 upon epsilon 2. And small body in a large enclosure. In a large enclosure. These are the special cases. It means A1 by A2 will be 0. If A1 by A2 becomes 0, use this expression. If A1 by A2 is 0 and F122 is 1, so it will become Q122 net will become sigma into A1 into epsilon 1 into T1 to the power 4 minus T2 to the power 4. Small body 1 in a large enclosure 2. So these are the expression, and if we equate these expressions with, so the general expression is Q122 net is equal to sigma into A1 into Fg into T1 to the power 4 minus T2 to the power 4. This expression, if we equate these expression, then Fg is called as gray shape factor. This is known as gray shape factor, Fg. Or it is called as equivalent emissivity. Equivalent emissivity. Or we can also call it as interchange factor. It is also called as interchange factor. And the last one is the shield. Let us talk about the radiation shield. The formula for radiation shield. N is the number of radiation shield of equal emissivity. Emissivity is equal to, let us say, epsilon 3. A1 is equal to A2 is equal to A3 is equal to so on. All the surfaces are having same area. So Q122 net with shield for N shield will be written as sigma into A into T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon 1 plus 2n by epsilon 3 plus 1 by epsilon 2 minus n plus 1. Where n is the number of radiation shield. N is the number of radiation shields having same emissivity epsilon 3. Epsilon 3. Epsilon 3 is the number of radiation shields. N is the number of radiation shields having same emissivity epsilon 3. and for epsilon 1 is equal to epsilon 2 is equal to epsilon 3 is constant. For all the surfaces are having same emissivity epsilon, then we can say Q for n shield is equal to 1 upon n plus 1 into Q without shield. Or we can say Q n shield divided by Q no shield, Q without shield is equal to 1 upon n plus 1. This is the relation. So that completes our formula list. 2 घंटे लग गए हमें. So that covers all the formula list. I hope you are able to revise those formula. किसी को कोई confusion, कोई doubt है तो do let me know. Otherwise, go through these formula again and again to make yourself comfortable. All these formula I have already discussed. So I will see you in another such session. Till then, enjoy. Take care. Have a good day. Have a good night and see you in the next session. So take care, guys, and keep preparing, keep revising the concept and do well in your upcoming examination. Thank you very much for joining in. Take care, stay safe. See you in the next class. Thanks a lot, guys. Thank you very much. I will share the PDF of this session to my Telegram group. I'm going to share the PDF also to my Telegram group. FM का जोशित सर लेंगे. Tomorrow FM will be there and Joshit sir from civil engineering branch, he will be taking the session. All right. हाँ formula मैंने लिस्ट दिखाई थी ना. ठीक है. So thank you guys. See you. Take care. Good night. Stay safe, stay motivated and all the very best for your upcoming examination.